Hey, Kathleen.
Okay, so today we're going to be going over problem 10.6 from the homework. So if you guys could open there. So we have this motor here, and you've got this basic motor circuit that is current controlled. So it says the figure to the right shows a motor with the rotor rigidly connected to the telescope, yada yada. And so we have the telescope's orientation theta is described by that that differential equation there. So we have all these parameters, so like mass, gravity, and we have our two state variables, or theta and the current. And then we have some external torque of a load acting on the motor. So first part A, says with T load equal to 0, wants us to find I nominal, the nominal value of I to keep theta equal to theta nominal. So if theta is our constant, if theta is our constant value, theta nominal, what is theta dot and theta double dot going to be?
Theta dot nominal, theta double dot nominal.
Yeah, that's right. So what about so if our nominal value is a constant value, what are those theta dot nominal and theta dot double dot nominal going to be?
0.
That's right. They're going to be 0. So if we cancel out some equation, so if we plug in theta nominal into our equation of motion, and we know that theta dot nominal and theta double dot nominal are 0, we're left with negative mg L sine of theta nominal equals km I nominal, because the load torque is 0. And so that means that I nominal is just negative mgl sine theta nominal all over km. Okay. So then part 2, or part B, I guess part 2 in the current version of the textbook. I want to design a control system. We want to write the ODE so that our theta, so we have theta tilde is our error, so it's theta minus theta nominal. And then I tilde is also our error of our current, right? I guess our actual current minus our nominal current. And so then using these definitions and the small angle approximation, sine theta tilde is approximately equal to theta tilde, and cosine of theta is approximately equal to 1. Find the linear ODE governing theta tilde. So we are going to use those two relationships. So we have theta tilde is equal to theta minus theta nominal, and our I tilde is equal to I minus I nominal. And we're just going to end up doing a substitution. So we're going to plug in our theta and I into that equation. So we're going to have theta is equal to theta tilde plus theta nominal, and I sorry, 1 second. I'm looking between two different versions of the textbook here, making sure things are right. Yeah. And so then I is equal to I nominal plus I tilde. Okay. So for that first term, the theta double dot term, we have I ZZ theta double dot. And if we plug in our substitution right there, what are we going to be left with? I times what? Oh, sorry, I see a chat from Kathleen. Oh, perfect. Okay.
Is theta nominal still constant?
Theta nominal is still a constant.
And is the error theta a constant as well?
So the error isn't constant, but if we take the derivative of this twice, we would get theta dot is equal to theta tilde dot plus theta nominal dot, and then do it again. Theta tilde double dot plus theta nominal double dot is equal to theta double dot. But like we said earlier, theta nominal dot and theta nominal double dot are going to be 0 because theta nominal is a constant term. So that is actually just going to be theta tilde double dot.
Okay.
Same thing. So that right there is just IZZ theta tilde double dot. Our term, so following the same process, we're going to get that the coefficient here is just b theta tilde dot because we make that substitution. Take the derivative, theta nominal dot is 0. So theta dot is equal to theta tilde dot. And then this last last term here, we have, so what we want to do, so I'm going to go ahead and write out our, let's see here. So normally, so we have that term as minus mg L sine theta. So I'm going to say dot, dot, dot. So those are our higher order terms, minus mgl sine theta. And that's equal to km I minus T load, right? And so we're going to make our substitutions here. So minus mgl, because we want this in terms of our theta tilde and our I tilde. Sine theta is going to be equal to theta tilde plus theta nominal. And that's equal to km, and that's equal to I tilde plus I nominal. And then minus T load. That's just a constant, so I'm not going to worry about that here. Okay. Questions about these substitutions that we're doing?
No.
Okay, perfect. I appreciate the response. So what we're going to do here is we want to see if we can get rid of these nominal terms. So we know that our I nominal, we already figured out right there. So we'll go ahead and substitute that in. So km I tilde plus km, and I nominal is equal to negative mg L sine theta nominal over km. And then for the other side, Does anyone remember the trig identity for sine of a plus b?
Is it like sine A times sine B plus cosine A cosine B?
Close. That's similar to the cosine one. It comes out to sine A cos B, cosine B, plus sine B cosine A. So what this comes out to is negative mgl sine theta tilde cosine theta nominal plus sine theta nominal. Sorry, I'm running out of space here, so it's getting kind of hard to read. Cosine theta tilde. Okay, do we follow that?
Yeah.
Okay. So then I'm going to distribute things, and we're going to apply our small angle approximation. So minus mgl so we know we're using the small angle approximation. So sine of theta tilde is approximately equal to theta tilde. And then we still have a cosine of theta nominal. And then minus mgl sine theta nominal. And cosine of theta tilde with the small angle approximation is approximately equal to 1. And that equals km I tilde minus, so I'm going to cancel my km's here, minus mgl sine theta nominal. So you can see that these two terms cancel out. And so we still have our constant higher order terms. So the iz theta double dot tilde plus b theta double dot tilde minus mgl cosine theta nominal times theta tilde equal to km I tilde plus T load. So this term right here is going to be a minus mgl cosine theta nominal. And this one is just going to be a k sub m. Okay.
Can you go back to the
Questions?
bottom really fast?
Yeah.
Okay, thank you.
Any questions about the substitutions that we did? The terms that were canceled, small angle approximation, anything like that? Okay. So now just the last part, we're going to complete the block diagram by labeling the signals for all of our terms. So I guess, how do we feel about block diagrams at this point? Do we know what the boxes and the signals mean? Anything like that?
I remember in class he said the boxes are like transfer functions and the circles are summations, but I can't make one myself, no.
Okay, perfect. Amelia, you about the same boat, or you have different feelings about? Feel the same? Okay, perfect. So block diagrams, they're always they're gonna have at least one input signal and at least one output signal. And signals are just numbers. So here you can see that the output signal is theta. The thing coming out is going to be theta. It's going to be a number. And yeah, sorry. So each one of these arrows represents a number coming out of the summing junction or out of one of these transfer functions, or really the boxes are just, more generally, they're just functions. So you give a signal into a box and a different signal comes out, and that's just a function. So this arrow right here is going to be our input signal. It's going to be our commands to the system. So what do we think with this control system that we've been talking about with our motor up here? What do you think we're going to command the system to do? What variable or number do you think is most useful to use there?
K sub m.
So K sub m is actually going to be, it's just a parameter. And so it's a parameter that we set. You're right, we do design that. That is a number that we choose. But K sub m is something that tells us how the system behaves, and we design how the system behaves. But the input, the thing that we actually want to command the system to do, is actually going to be a theta. We're going to say, hey, motor, go to this angle. Right, theta nominal. Good catch, Amelia. We're going to say, motor, go to our desired theta nominal. And then it's going to do all of this with all the boxes and circles and arrows. And it's going to spit out, hopefully, the right theta at the end. So if we have, into this summing junction, we have a negative theta nominal, and we have this theta coming all the way around here and going positive into that summing junction. We're going to have theta minus theta nominal. And so then what comes out of that summing junction?
Theta tilde.
That's exactly right. So that signal, that number right there, is theta tilde. And so then, let's come up this signal here. We give, so we put theta nominal into this function right there, that minus MGL sine theta nominal over Km. What comes out of that function?
I nominal.
Wait,
That's
what
right.
did you ask?
What comes out of this function right there? And that was right. I think it was Kathleen that said I nominal. And that's right. So that's the same function that we have written up here at the top. And I nominal comes out of that function. So let's go back to go back down below here. So theta tilde comes into our control law and something comes out. What is our control law here? Do I have it written? So our control law is essentially what picks our, so it takes our error, our theta tilde, and then it takes our error and then decides, okay, I need to put this much effort or this much force or this much current into the system. So what do you think would come out of that control law? Any ideas at all? Doesn't have to be right.
Would it be some type of current?
It would be the type of current. Very good. So it's actually going to be I tilde. And so that's our, so in this case, we have theta nominal and we have an I nominal. And if we give a theta tilde is our error in theta, we're going to get back our error in current. So I tilde is correct. So then we have this summing junction here. So after the control law and that I tilde, that goes into a summing junction. I nominal also goes into that summing junction. So what is I tilde plus I nominal going to give us?
Just I.
Mm-hmm. That's exactly right. It's just going to give us I. And then you multiply I by Km, and what is that going to be? So it's not exactly here anywhere. So I by Km is right there. That's an input to the system. They also tell us that we can use this Tm on our block diagram. So I times Km is the torque that we're going to be giving to this motor. So we command the current, and I times Km is going to be the torque that the motor feels. And then we add that torque to any loads and throw it into the plant. And the plant is just our telescope, I think is what we're calling it, moving around on the motor axis. So that's our dynamics. So we give Tm plus T load into our motor, and then that's going to describe the theta that comes out. Any questions about this this block diagram here?
No.
Can you explain the control law part again? Like passing theta tilde in and getting I tilde out?
Mm-hmm. Yeah, so a control law is so a more basic block diagram than this one is going to be, you have some input signal, and that's going to go into a summing junction, and then you're going to have your error goes into a control law, and that turns your error into some system input. I'll say SI. So this is I for input, error, and then you have your plant. And then coming out here. And so your control law is anything that takes in either your error or a commanded signal. It doesn't have to be a closed loop. You can just go straight into a control law and straight into a plant. And then out, and that's an open loop controller. But your control law is what takes your commanded signal that you can measure, that you understand, that you know, like I want this. So in our case, we want a certain theta nominal, and then we get an error. And so the control law is what takes that error or that input signal and turns it into something useful for our dynamics. So in this case, we have a theta tilde. That's not very useful for commanding our circuit. to do something. So it takes the theta tilde and then it does the math to figure out what current we should be giving the system. And so that's usually, that's what you have design power over, is your control law. Because your plant, you probably can't change it, requires either changing hardware or you can't change it at all because it's a physical natural system. But your control law is how you manipulate your signal that you give to your plant. Does that clarify that, Kathleen?
Yeah, thank you.
Okay. So yeah, it's a very broad term in this case. In your version of the textbook, this is called your nominal control. And this is called your error control. So it's just taking in the error and spitting out your error current. Okay, any other questions? Okay, I have 10.7 here as well. I didn't prepare as much for this one, so we can go ahead and start working through this if you guys would like, or we can go ahead and cut early, whichever you would prefer.
I don't mind working on it.
Okay, we'll go ahead and keep going. So this one, exact same system. So we have a current controlled motor. So now what we're gonna do is we're gonna do a proportional derivative feedback control law. So this is our control law here. So I tilde is equal to minus Kp tilde minus Kd tilde dot, or theta tilde dot, where Kp and Kd are the proportional and derivative feedback constants. So we're going to substitute I tilde into our ODE equation and rearrange it. So we have, going to try and, maybe I'll try and zoom out a bit so I can see. So IZZ, theta tilde double dot, plus B theta tilde dot equals Km, and we're going to substitute in I is negative Kp theta tilde minus Kd theta tilde dot minus T load. So then we're going to go ahead and rearrange things here. So we have IZZ theta tilde double dot plus, and we're going to have a B plus Km Kd theta tilde dot and then we're going to have plus Km Kp theta tilde equals minus T load. Any questions about that?
No.
Okay, so that's our answer. We have, try and write small here. So I, Z, Z, theta tilde double dot. Can I make this smaller? No. Plus B plus K M K K D theta tilde dot plus Km K P theta tilde. Okay. So now it says express Kd and Kp in terms of IZZ, B, Km, and the damping ratio, and the natural frequency omega n associated with this differential equation. Okay. So we know so what do you remember the form of the second order equation that has our natural frequency and zeta in it?
Yeah.
Can you tell me what it is?
Plus 2 zeta omega n theta tilde dot plus omega n squared theta tilde.
That's right. Okay. So in this case, we have to divide both sides here by IZZ because we have to have a 1 in that first coefficient. So we have theta tilde double dot equals B plus Km Kd over, oops, not equals, plus B plus Km Kd over IZZ theta tilde dot plus Km Kp over IZZ theta tilde equals negative T load over IZZ. Okay. So now, so we want Kd and Kp in terms of system parameters and zeta and omega. So we just have to isolate that isolate Kd in that term. So so 2 zeta omega n is equal to, whoops, sorry. 2 zeta omega n is equal to B plus Km Kd over IZZ. So we just have to multiply both sides by IZZ. So 2 zeta omega n IZZ. Go ahead and subtract B and then divide over Km. And that is our KDD, or KD. Any questions about that?
No.
Okay. Next one, so omega n squared equals the coefficient in front of our theta, so K m Kp over IZZ. So omega n squared IZZ divided by Km equals Kp. So omega n squared IZZ over Km. Okay. Questions about that? Okay. So now, as a control systems engineer, you are tasked with finding values of Kp and Kd that satisfy each design specification in the following table. Express your results in terms of IZZ, B, and Km. So if we want our error between theta and theta nominal to be critically damped and a natural frequency of 2 radians per second. So what is our zeta value if we're critically damped?
1.
That's right, equal to 1. And then our natural frequency is 2. So Kp, so they've already done K d for us, but Kp is omega n squared Izz over Km. So 2 squared is just 4 Izz over Km. All right, the next one. So theta tilde has a decay ratio of 0.7 and a period of 3 seconds. So what does that mean? So a decay ratio of 0.7 and a period of 3 seconds. What does that mean for our zeta and omega n values? Does anyone have these equations remembered? Can go in your textbook, open up to page, I believe it's 42. Nope, 42 is literally a blank page. Page 40. Not quite. Decay ratio.
39? Maybe.
Yep, I'm looking at 39 here. So let's see. So our period. So we know that our log decrement is equal to our, oh, so there's one. So if we're looking on page 39, our log decrement is equal to the negative natural log of our decay ratio. And then what can we do with our log decrement?
Using theta equation under that. So like square root divided by 4 pi squared plus log deck squared again, and then square root.
Mm-hmm. That is right. Sorry, my iPad went to sleep, so the screen share went away.
Just look in that table on 39 instead of going to the log decrement, or can we not do that?
Oh, look at that. Yeah. So we want a decay ratio of 0.7. So yeah, you can go straight to the table. So our decay ratio is 0.05, or zeta becomes 0.057. This do not disturb thing does not work. And then we want a period of, so we know our period is 2 pi over omega d, right? And what's our relationship between omega n and omega d?
Omega d equals omega n times the square root of 1 minus theta squared.
Mm-hmm. That's right. Okay. Does anyone have a calculator on them? Let's see here. Go ahead and pull out a calculator. So our KD is equal to zeta omega n I z z minus b over km. So zeta is 0.057. Omega d
I got 0.9983 for omega d.
for omega d. So you did 2 pi over 3.
Oh, I might have done that wrong.
Yeah, it should be somewhere around 2, right? So 2 pi divided by 3 is about 2.09 for omega d. And then we're going to divide that by the square root of 1 minus 0.057
Okay, now I
squared.
got 2.09, sorry.
Yep, 2.09781. Never got a chance to round that off. Okay. All right, so we have 2 times zeta is 0.057 times 2.09 equals 0.239. So that's about 0.24 IZZ minus B over KM. Okay. I'll go ahead, in the interest of time, unless you would like to do the next two, I'm going to go ahead and skip the next two and go on to part D. Is that all right with you guys, with you?
Oh, that's fine. Can you show how you got that 0.24 just for a second?
Yeah, so I
It's
just
that
have
last
2
step.
zeta omega n. What was that?
Just the last step.
Yeah, so this is my equation right here. It's 2 zeta omega n IZZ. So I know zeta is equal to 0.057. And omega n is equal to omega d over square root blah, blah, blah. So that's 2 pi over 3 over square root 1 minus zeta squared, which is 0.057 squared. And so 2 zeta omega n with this zeta and this omega n comes out to the 0.24.
Okay, thank you.
Okay, so part D, to minimize steady state error, controls engineer proposes a PID control law of that form. Substitute I tilde into the equation of motion, then differentiate it and rearrange to standard form. So we have our equation of motion up here. So similar process to what we did up above for part A. Let me go ahead and come over here to save space. So we have I z z theta tilde double dot plus b theta tilde dot equals k m I tilde minus t load. I tilde is equal to that. So that means we've got I theta tilde double dot plus b theta tilde dot equals k m times minus kp theta tilde. minus ki integral t equals 0 to t the tilde dt bar minus kd the tilde dot. Okay. Minus t load. So now we will go ahead. So it says substitute I into the equation of motion, then differentiate it. So we're just going to take the time derivative. So we have I theta tilde triple dot plus B theta tilde dot equals Km. And so we just have Km multiplied in. We take and we scale a derivative. The derivative is the same. So that's minus Kp theta tilde dot minus Ki. And we just take the derivative of this integral is just whatever's inside the integral. So theta tilde minus Kd theta tilde double dot. That is now a Kd. Minus T load. So now I'm going to go ahead and rearrange. So I have I theta tilde triple dot. Everything okay?
Would T load not like cancel out or disappear?
Can you repeat that? Sorry.
I was saying, would T load disappear since we took the time derivative?
Oh, it's a good question. Oh, it's going to be a T load dot. Sorry. So T load is not necessarily constant, but we're just going to take the time derivative of it. Good question. So plus, and let's see, so our theta dot terms, so we're going to have a B plus Kp Km theta tilde dot. I guess we're going to, there's a theta tilde double dot that comes over, so sorry about this. This is not in order, but a Km Kd theta tilde double dot. And then bringing over just the thetas, so plus Km Ki theta tilde. And that's equal to minus T load dot. And that comes into here, so IZZ theta tilde triple dot plus B plus Km Kd theta tilde double dot plus Km Kp theta tilde dot plus K, oops, Km Ki theta tilde. Questions about that one? Okay, so this last bit right here, really quick. The advantage of a PID controller over a PD controller for minimizing steady state error in response to a constant load is that a PID control, do you know what PID control does to steady state error?
Doesn't it make it go to 0 or something?
It does. It eliminates the steady state error. And that's because you have, if you're integrating your error over time and your input force is proportional to that integral, if you have an error, then that integral is just going to keep getting bigger and bigger and bigger. And so you're going to keep increasing your torque or your input torque until that integral stops growing, which is when you have 0 steady state error. So it eliminates steady state error, SSE. So one disadvantage of the PID control is the resulting ODE is what order? So what order is that ODE that we just wrote?
Third.
Right, it's a third order ODE, whereas the one resulting from PD feedback control is just a second order. So it adds a degree of complexity to our system here. And so we're solving a third order system versus a second order system, which is just a level of complexity that you may or may not be prepared to deal with. Okay. Any questions about that?
No.
Okay. Go ahead and stop the recording.